Hello, Circuits 1 class. I am about to cover Wheatstone bridges. And the most important thing to understand about a Wheatstone bridge is that you don't see them very often. You'll see them with strain gauges measuring force or load as instruments or as other instrument type amplifier inputs. So you want to understand basically how they work, but it's not something that's going to come up a lot. Of course, it'll probably show up in your first mechanical engineering course in measurement and instruments, and if you tell them that I said that, I'll deny it. All right, so I'm going to draw a Wheatstone bridge so that it looks like something you might have seen. Pair of parallel resistors. Maybe you haven't seen it in this class yet. So a Wheatstone bridge is used to figure out the resistance of a device that you don't know the resistance of, Rx. And what you do, you put something like one of these D'Arsonval movement or galvanometers, something that measures the voltage or the current through this across this barrier. And if I'm going to mark all of these currents, I1, I2, IX, and I3. So what you do is you adjust R3 until this voltage goes to 0. This meter, this is shown as a voltage or current meter, shown in another video, discussed in another video. When you get the current in this meter to 0, when the current is 0, the voltage here is 0. When the voltage is 0, the value of Rx will be given by R2 over R1 times R3. If I could just give you the formula and walk away, that would be great. But there are so many problems in this book where they throw Wheatstone bridges at you under hidden guises that I need to go through the development or the derivation so that you have a hope of understanding it or believing it. All right, so when I adjust R3 to a point, assume it's possible to adjust R3 to a point where that current equals 0. And when that happens, I1 equals I3 and I2 equals IX, because Kirchhoff's current law says so. If that's 0, I1 equals I3, I2 equals IX. So let's presume that we can get it to that point, and we're going to write Kirchhoff's voltage law around this loop and this loop. So let's do that. I drew my plus here, my minus here for the voltage across R3, and so now when I go up through the loop, I'm going to say negative I3 R3 plus IX Rx equals 0. IX Rx equals I3 R3. That's loop 1. Just solving for Ix. Now I'm going to do loop 2. Loop 2. Negative I1 R1 plus I2 R2 equals 0. So I2 R2 equals I1 R1. This is true when IM equals 0. And if I label these nodes A and B and V and C, label as A, B, and C, when VAC equals VBC, when VAC equals VBC. Because if I have the same voltage from here to here and the here to here, when I do Kirchhoff's voltage law, the voltage from here to here, then VAB equals 0. Okay? If you do Kirchhoff's voltage law and you solve for VAB at this point, VAB equals 0. IM equals 0. No current in this branch. And when that happens, this formula will be true. So we're going to prove it over here. All right, I have IXRX equals I3R3, I2R2 equals I1R2. I'm going to take L1 and divide it by L2. I can do that, right? I can take, since these two are the same on either side and these two are the same on either side, I can divide this by this, and I get Ix Rx over I2 R2 equals I3 R3 over I1 R1, and this is when, when Im equals 0, and I1 equals I3, Ix equals I2. When this is 0, this current goes straight through here. And since Ix equals I2, I can divide out Ix over Ix. And so I end up with Rx over R2 equals R3 over R1. Rx equals R3, R2 over R1. The neat thing about Wheatstone bridges is you could use a crude voltmeter or a crude amp meter, and it could have a very low resistance, and you can still get very accurate measurements of Rx by just adjusting R3. And also, let's say that Rx is a very, very high resistance. You can use a very high resistance in R2 and then have R1 and R3 completely different ratios, and it'll still work. So this is the relationship you're looking for, and that's how a Wheatstone bridge works, and we're just proving it. All right, so there's an example in the book for a Wheatstone bridge. There's other examples. I won't go through them here. Well, a little bit later when we do node and node voltage and mesh currents, you'll see some other Wheatstone bridge examples. But you notice how I drew it. I drew it as two parallel resistances. And if you looked at it in the textbook, it looks like a diamond. It's shaped like a diamond. Don't be fooled by the shape of a circuit. All right? Don't be fooled by the shape of a circuit. Don't be fooled by the shape of a circuit. That's a rule I have. If I say it 3 times, it might be on a test. I might try to fool you with the shape of a circuit. All right, so there you go. That's it for Wheatstone Bridge.